Thank you, Peter. And next we have Diederik Kingma, who's going to talk about semi-supervised learning with deep generative models.
Hello everyone, this is work with Max Welling in Amsterdam and Shakir and Danilo at Google DeepMind in London. One of the most common problems in machine learning is that of semi-supervised learning, where we wish to learn a classifier, but not all of the data points are labeled. So how to make optimal use of both the labeled and the unlabeled data? We introduce a principled probabilistic approach to semi-supervised learning that is very powerful and can be used in combination with almost any existing deep learning classifier. So how does it work? A classifier learns the function from the input x, for example images, to class labels y. However, a more realistic model of how the data was generated was that the class label came first, and then the input image x was generated from the label and other latent variables z. So what we do is we introduce a generative model that we parameterize with deep neural networks that actually learns this function from the label and other latent variables to the input x. To learn the parameters of this function, we're going to need to do posterior inference over the latent variables, which is also the label in case of the unlabeled data. And we're going to use the classifier to do this approximate posterior inference. So the classifier not only needs to do the correct classification for the labeled data, it also needs to do the correct approximate posterior inference for the unlabeled data. And this second purpose acts as an effective regularizer for the classification model, leading to much lower prediction error on new data. Our method is also very efficient and scalable because of recent advances in stochastic variational inference and stochastic backpropagation. All that is required is the optimization of a single objective function using standard stochastic gradient descent. It's very simple. We see that in experiments we often need about an order of magnitude less labeled data than other approaches to get good classification error. For example, on MNIST, where we have only 10 labels per class, we reach an error of only 3%, while the previous state of the art was 12% error. So that's a pretty large reduction, and we also see good results on other benchmarks. What is also cool is that we can do very successfully analogical reasoning using our efficient approximate inference methods. For example, you can take an image, then you can infer the style and the class, then you can change the class label and generate the whole sequence of images that looks like the input image, but just has a different class label. So this is a form of analogical reasoning. So for more information on our approach to semi-supervised learning, that is very flexible and powerful and can be applied to almost any existing classification model, please see our poster. Thank you very much.
Thank you, Diederik. And last we have Karen Simanian, who is going to talk about two-stream convolutional networks.